All right. Um, so yeah, okay. So continuing from where we left off, we were looking at arithmetic expressions, and in particular, we were looking at subtraction. Um, so the last thing we saw was encoding subtractions, and we saw some examples. And the next thing we are going to see is equality. So I want to take two Church numerals encoded in lambda calculus, and I want to say, I want to check whether they are equal, right? So if I gave you subtraction, and I gave you, say, a language like C, um, and we already have seen the is0 function, right? So we want to check whether a number is 0 or not. So if I gave you subtraction and is0, then you can implement equality by something like this, right? A test like this, where you subtract one number from the other. If the result is 0, then we know that these two numbers are equal, right? So this is what we can implement if I gave you integers, but we operate on natural numbers, right? In particular, as we had seen earlier, I think here, so if I do 2 minus 3, I get 0 back because I don't have negative numbers encoded in natural numbers. So if I do 3 minus 4, I get 0. So if I directly apply the encoding that I have here, then I would consider 3 equal to 4, right? So this is not what we want. And what we do want is this, right? If both m minus n is 0 and n minus m is 0, which can only happen if the numbers are the same, right? Then we can say m equals n. So in this case, 3 minus 4 will be 0, but 4 minus 3 will be 1. So m is not equal to n. So this is how we encode equality, arithmetic equality in natural numbers. Yeah, Anirudh. Yeah. So that's really what we want. The definition of equality is defined using all the operators here, right? Is 0, subtraction, and logical conjunction, all of which we have so far built up, right? So we can implement is 0 as first checking whether m minus n is 0, and then n minus m is 0, and we have a conjunction here. And so if both of these cases are true, then the result is equal. So that's how we encode equality. Okay, so I can ask for equal to 2, so I'll get true. I can ask for whether 3 minus 2 is equal to 2, right? I'll get false. I can also ask whether 2 minus 3 is equal to 0. Yeah, so this will be equal to 0, right? Because we have natural numbers encoded. So 2 minus 3 is 0. So 0 will be equal to 0. So that's why we get true here. Okay, so far we've seen a lot of arithmetic, right? So we will step up a little bit, right? So the thing with lambda calculus that I told you earlier was it is as powerful as a Turing machine, right? So when I say it's as powerful as a Turing machine, it is a Turing complete language. And if it is Turing complete, we one of the defining features is we should be able to encode a non-termination in the language, right? Um, and we have seen an example of non-termination, this omega operator that we had seen earlier, right? Where you can keep reducing and we will never reach a beta normal form. And that sort of hints that we can encode non-termination here. So the question then is, okay, so um, you can define regular functions, right? Anonymous functions and applications and so on. But one powerful way of defining functions that do useful things is recursive functions, right? I want to encode recursion in lambda calculus. Only then will I be able to express something like loops and so on. So how can we encode recursion, right? The hint is that we can encode non-termination. So we are going to use this idea that we can encode non-termination in order to implement recursive functions in lambda calculus, right? This is also encoding. So we'll have to come up with a clever scheme for encoding. And here's the clever scheme, right? So before we look at how we encode it, I will introduce this concept of fixed points, right? So given a mathematical function f and some value x, we say that x is a fixed point of f if f of x is x, right? We just call that a fixed point for f, right? An example is consider f of x equals x squared, right? This function f of x has two fixed points, 0 and 1. So 0 square is 0 and 1 square is 1. And there are also functions which don't have any fixed points, right? So here is a mathematical function, which is the successor function. So whatever value of x that you provide this function, it will always return a value which is not x, right? So this particular function is set to not have fixed points, right? A very curious fact about lambda calculus is that every lambda calculus term has a fixed point, right? So any lambda calculus term that you can write has a fixed point. What do we mean by fixed point for lambda calculus? So for lambda calculus, a term n is said to be a fixed point of f, right? If f of n equals n, where equality is beta equality. So you can reduce f of n to n, right? So that is meant to be fixed points. This is a very curious fact, right? In untyped lambda calculus, for every f that you can pick, there is always an n that I can pick that is a fixed point, right? This should sort of tempt you, right? Because I can write simple functions like this which have no fixed points, but I'm saying I can always find a fixed point for any arbitrary lambda term f, and we will see how that works, right? And we go back to our favorite omega operator. So let's consider d to be lambda xx, right? Lambda x applied to x, and omega is basically d applied to d, right? It's self-application. So I have a d, I apply it to d. So if you apply d to d, all you get back is the same term, right? Which is lambda, which is omega. And this is what we've seen earlier, right? This is the omega operator. If you try to beta reduce it, you get the same omega operator again. And this, if you try to beta reduce it, until you reach a beta normal form, the procedure will not terminate. It will go into an infinite loop, right? So we can sort of use this omega operator, modify it a little bit to come up with this new operator called Y Combinator, right? So Y Combinator is this operator. So omega is lambda x applied to x, lambda x applied to x. Y Combinator adds a little bit of additional terms on top of omega. So we have an outer f, right? That's the function for which we are going to compute the fixed point. And we introduce a f around this x applied to x, and the same way here, x applied to x, right? So just compare these two, right? It sort of looks similar. It behaves very differently. The only reason why I put these two things next to each other is that we are going to use this idea of self-application, right? This is known as the Y Combinator. There is a very famous incubator called Y Combinator. I think some of you may know it. It's a startup incubator. It's been very successful, right? So Paul Graham was one of the people who started that, and Paul Graham has made like lots of investments in large companies now, Uber and Facebook and a bunch of companies which have went on really well. He's a functional programmer, right? So he started writing Lisp, and he still writes Lisp a lot. And this Y Combinator website is written in Lisp. At least one of the backend is Lisp. Okay, so that interesting anecdote aside, let's look at what Y Combinator can do, right? So here is Y Combinator applied to arbitrary function f. So this is some lambda term f. I don't care what that term is. I'm just going to consider f as an abstract thing now. So what happens if I apply Y Combinator on f? I can try to beta reduce it, right? So the first thing I'm going to do is substitute this big F for small f, right? Wherever you see big F in this term, you substitute that, right? So we get big F here, and for this small f, we get big F, right? And this is self-application now. So reduce it one step, one further step. So take this term, substitute this term wherever x is. So you get the outer f, right? And you get the same term repeated twice, right? But if you sort of stare at this term, right? This term, the highlighted term LO, is the same term as the term here, right? So it's the same exact term. So we know that we got here by reducing YF. So write this term, replace this term just by YF, right? And what you end up getting is FYF, right? So this F on the outside stays the same. We know that we got here by reducing YF, right? Because YF reduces to this term and this term is the same as this. So you can write this as FYF. And if I write it out, so I have YF equals, right? Equality here is beta equality equals FYF. So if you sort of stare at this, right, you can sort of think about this as x equals f of x, right? Where x is YF. So this YF, right? This YF is said to be the fixed point of f, because for any f, I can always create a YF because I know what a Y combinator is, and I don't assume anything about the structure of f here in the Y combinator application, right? So YF is said to be the fixed point of f, right? Given any f, I can always create a YF which is going to behave as if this equation describes, right? If you apply f to YF, it's the same as YF, right? So, and you can keep expanding this one. That's the whole point. So you have a YF which is equal to FYF, and we know this YF is equal to f of YF, and what you end up getting is multiple applications of f, right? And this is sort of lies at the core of recursion, right? You can keep expanding it as much as possible. So you can use Y Combinator to achieve recursion, right? So, so the takeaway here is just like mathematical functions had a x equals f of x, where if you had a x equals f of x is said to be the fixed point of f. For any lambda term f, you can always get a YF such that YF is the fixed point of f, right? And Y is the Y combinator. Okay, so that's the key bit here. So how do we use this to get recursion, right? So here is functional programming 101 program, right? So when you start writing functional programs, this might be one of the first programs that you might encounter online, right? So write a factorial function, right? The usual recursive factorial function. What I've done in this lecture so far is I've sort of built up all of the operators that are necessary in order to encode this function. So we've seen equality, right? We've seen is0. We've encoded the natural numbers, right? We've also seen multiplication. I also showed you predecessor, right? And we're going to see how recursive function application works, right? Okay, so this part should be familiar, right? Oops. This part should be familiar. So factorial takes a natural number. If n is 0, then factorial of that is 1. Else, it's n times some f of n minus 1, right? And what is this f? This f is supposed to be the function call used for the recursive case, right? In OCaml, this would just be factorial, but we will just make it explicit here because we are going to apply it through the Y Combinator. Okay, so just assume that this is just a recursive version of fact, right? Fact is just this whole function, but think about this f as the function that you're going to call for the recursive case, right? So the second argument is the integer, right? And the first argument is the function call for the recursive case. And we will use Y Combinator to actually tie the knot. So we want to say this f is actually the function that we have here, and we are going to use the Y Combinator for this. So how are we going to use it? It's easiest to just look at an example, right? So we are going to make factorial, this factorial definition recursive. So the way you do that is apply Y Combinator on fact, and then I'm going to trace the execution of fact applied to 1, right? Factorial of 1 is 1. We know that. We're just going to see how that expands out, right? So this is Y of fact. And we know that any Y of f can be expanded to f of Y of f, right? That is what we've seen here, right? Given any Y of f, you can always beta reduce it to f of Y of f. So I get fact of Y of fact of 1, right? Now I have a function definition here, and then I have two arguments, right? Argument 1, argument 2. I'm going to apply these two arguments to the definition here. So the definition here is, I can actually copy paste this for simplicity. So let me copy it, paste it here. Okay, so fact we know is this particular function, right? So you apply wherever f is there, you apply y of fact. Wherever n is there, you apply 1, right? If you expand it, n is 1, so you have 1 equals 0, then 1, else n is 1, right? And f is y of fact, so you have y of fact of n minus 1 is 0, right? So you get 0 here, right? So we have also seen if then else, we know how to do test, right? So 1 equals 0 is false, so you get the false branch. So you have the false branch here. Expand y of f once more, right? So you get from y of fact, you get the fact of y of fact applied to 0. Do this beta reduction once more, right? The same application here, right? So you have y of fact, substitute wherever f is there, and then you have 0 here, substitute that wherever n is there. So you get 1 multiplied by, if 0 equals 0, then 1, else 1 into y of fact of 0. Now 0 equals 0 is true, right? So you get 1. So 1 times 1 is 1, right? So that's how we get recursion out of this Y Combinator. The one thing to consider here is we've been very careful about when we go ahead and reduce Y of fact, right? I'm not keeping on reducing Y of fact. Here I could have chosen to reduce Y of fact, but I did not choose to reduce Y of fact. I said, okay, I will do the application here, right? This is important, and we will come back to this. Okay, so now I've showed you how this works. We can actually encode it here, right? This is the function that I'm going to encode. So this is the Y Combinator, right? I've just written down the Y Combinator here. I'm going to write down the factorial function. So the test here is n equals 0, right? So I have a is0 variable n, right? That's the test here. And then I have the false branch. What is a false branch? False branch is n multiplied by, so you have multiplied n and f of n minus 1, which is application of f applied to predecessor of n, right? That's the false branch. And the true branch is just 1, right? So you can just build it up. So test, so the test here, true branch is 1, false branch is fb, false branch here. And that's the factorial function defined for you. So now you can ask for factorial of 2. You get 2 out. You can ask for factorial of 3. Takes a long time, right? So actually this terminates of non-termination, because I have a depth limit of 10,000 by default. You can increase the depth limit by 10 times. This would work out. Just to show you that this works out, right? 1, 2, 3, 4, 5, 6. Factorial of 3 is 6. So you can try 4. It will take a long time, right? So Lambda calculus is sort of useful for encoding these features, but it's not a practical thing for compilation, right? You don't want to directly interpret Lambda calculus as we've done. right? Encoding everything in lambda calculus. That's not a thing that we do in the real world. If you try 4, this won't terminate, right? So that is, or it will take a long time to terminate. So we've actually encoded a non-trivial function here, which is factorial. Okay, so Y Combinator is how we achieve this recursion. Okay, so here is a question, right? Y Combinator, which is just the Y Combinator here, is a fixed point combinator under which of these reduction strategies? Is it call by value, call by name, or both, or neither? What do you think is the answer? You can take a guess. I think that's fine. No answers. Okay, I will tell you the answer. The answer is call by name. Why? Because under call by value, right? So if you look at this particular example, if I look at a particular example, I started with y fact of 1, right? And call by name, I can expand it once, right? And then I can say, okay, now apply this term to fact. But in call by value, what will happen? In call by value, you have to reduce the function term and the argument term all the way, right? Both of them have to be in beta normal form before you can apply it, right? That's how call by value works. Just think about how you would do this in OCaml, right? If I have, say, f and then g of 10, I would reduce g of 10 first to a value and then apply it to f. But we know for a fact that if you keep expanding yf fact here, you can keep on expanding it on and on, right? So if you use this in call by value, anytime you find a y of f, you can keep expanding it forever and ever and ever. This will never terminate. So this particular program, right? The program here terminates because I'm using normal order reduction strategy, right? Which doesn't force the evaluation of the argument term, right? It only forces, it actually forces application whenever you can do an application. So in call by value, Y Combinator is not useful. It will just lead to non-termination, right? So what do we do about call by value? So is it the case that we cannot have recursion in call by value? No, we can have recursion, right? We have a combinator called the Z combinator, which is, the intuition is it is just a eta expansion of Y combinator. What is eta expansion? So consider the Y combinator, right? The Y combinator is just what we've seen. All we are going to do in Y Combinator is, this is some lambda term, right? This is just called M. And we had studied Eta Reduction, where we said if you had a function that is abstraction that is lambda y, M of y, you can always reduce it to M, right? Recall the last few slides of the previous lecture, where we said if you had a lambda x, mx, you can always write it as M. And we had also seen this example of sine, right? Lambda x, sine of x is eta equivalent to sine. And that is precisely what we are doing here, right? We take the Y combinator, and then what we do is we have a term x applied to x here, right? What we end up doing is we add a y to the front, right? We add a lambda y to the front and we apply y here. This is serving no use at all except stopping the evaluation, right? So we will see how that works, right? So you can go from Y Combinator just by eta expanding the correct term here to Z. So, okay, so I haven't told you what Eta Expansion is. So we've seen that Eta Reduction is lambda x, mx to m. Eta Expansion just goes the other way. Given any term lambda m, pick a fresh variable x, right? Which is not a free variable in M, and then you can write it as lambda x mx, right? So that's the idea. So just to write it out instead of just doing words, if you have an M, you can eta expand it to lambda x mx, right? Where x is a free variable, x is not a free variable in M. If x is a free variable, then it gets captured here, right? So this binder binds it. We don't want that. So this is known as Eta expansion. And if you go the other way, it is Eta Reduction. Right? If X is a free variable, X is not a free variable, then of M, then you can go the other way. Okay, so that's what we're doing with the Z Combinator. So just to see how it works, just like we did earlier, right? So we applied Y of F, now we do Z of F. We are going to substitute for small f, this big F. So we get lambda x f of this term, right? The same term repeated twice. This is self-application. So where x is found, substitute this right-hand side term, right? There is x, one x here, another x here, right? So you get the same term repeated twice. So you get the term repeated once here and then twice here, right? And you get the y again here. Just like we did for Y Combinator, this highlighted term, this yellow term, is the same as the previous term here, which we know is ZF, right? So you can write this as ZF. Okay, so now what we end up having is, it is f of lambda y ZFY, right? All that has happened compared to Y Combinator, you would have had something like f of y of f, right? But in Z Combinator, if you use the Z Combinator, then we get this extra y in the front, this lambda y and y. And this prevents further evaluation of ZF until it is applied, right? Until you apply some y here. Why? Because in both call by name and call by value, we don't reduce under the lambda abstraction, right? So we don't evaluate within the body of lambda. So this works out. And this is precisely what we want to do to prevent further reduction, right? Whenever you want to suspend the evaluation of some expression until it is applied, you just add a lambda to the front. And that is what we are doing here. And you can use Z Combinator for both the call by name and call by value. It will work out just fine. But it will not work out for normal order reduction, because actually it will work out for normal order reduction, because if f is a lambda abstraction, it will work out. So Z Combinator is like is the thing that you can apply for any reduction strategy, right? So yeah, okay, so that's Z Combinator. So okay, so that sort of is what I wanted to say about recursion in lambda calculus. So the key takeaway there is we use the fact that we can encode non-termination in a clever way to encode recursion, right? So we've actually written something non-trivial using just the lambda calculus that we had seen, right? So we've taken multiple steps, but the idea is that we've encoded a non-trivial program, factorial, just using the primitive lambda calculus expressions. So okay, so the last thing that we are going to see in this encoding part of lambda calculus is recursive data structures, right? So we've seen pairs, but pairs are non-recursive, right? So pair is just taking two types and then putting them together. But in OCaml, you have algebraic data types, right? We've written lists and trees and all these expressive data structures. You can sort of encode any arbitrary interesting structure that you want with algebraic data types. And if lambda calculus can encode everything, then it should be able to encode lists as well. So we are going to encode lists using just the lambda calculus encoding, right? And this covers, you can sort of take away this idea and apply it to arbitrary recursive structures, lists, trees, B plus trees, anything that you want, right? And we're going to use an encoding here where we take the constructors of lists or any other recursive structures as arguments in the lambda encoding. This encoding is called Morgenson-Scott encoding, right? So the key takeaway here is we are going to take the constructors as arguments. So how does it work? So what are the two constructors of lists? There is a cons constructor, there is a nil constructor, right? And if you want to encode a data type using lambda calculus, there might be several constructors, right? Take each of those constructors as arguments, and that's the key idea here. Okay, so how does it work? So for list, we have two constructors. C stands for the cons constructor, right? And N stands for the nil constructor. And nil value is just the nil constructor. So I'm just going to return N for the nil value. So what does the cons function do? So cons is, what is cons? Cons, you can write cons in OCaml as xxs, right? And does, so this is what I'm going for, right? So it takes a head and a tail, and then returns you a list that has x for head and x is for tail, right? So it takes a head and a tail, h and t, right? And then this is the encoding of the list as a data type. So every list takes the two constructors as arguments, the cons constructor and the nil constructor. And what are you doing here, right? I'm just applying the cons constructor to head and tail. I'm sort of saying, okay, that's the entire construction of what a non-empty list is, right? And this should sort of remind you of how we encoded this encoding, at least should remind you of how we encoded natural numbers, right? So that's 0, and this is similar to 1, right? But it has other things going on. But the idea is that we are applying a similar idea to 1. Okay, so this is sort of the 0, and this is additional data that is present, right? In natural numbers, we did not have any other additional data that is sitting in, but here we have some additional data that is sitting in. Otherwise, it is similar to how we encoded the successor operator, right? 1, 2, 3, 4, and so on. Okay, so that's the encoding, right? And the interesting bit is what we do with this encoding. So here is a list that has 2 and a 1 in that order, right? In OCaml, this would be a list that has 2 and 1. So how do we do it? So you have a nil constructor, right? And I build a list with a singleton list with 1, right? I do an application here. I take that list and then I append the 2 to the front, right? So I cons 2 to this list. So this L2 list is the same as 2 semicolon 1 in OCaml. Okay, so that's the list. So, okay, so what do we want to do with lists, right? So we've put it together, we've constructed the list. So we want to also extract the values out. I want to destruct the list, right? So what are the 2 ways of destructing? So you can sort of imagine you want to implement equivalent of the head and tail functions in OCaml, right? In OCaml, if you ask for the head, you just get the head element. Otherwise, it throws an exception. And if you ask for the tail, if the list is non-empty, then you get the tail. Otherwise, it throws an exception, right? We don't have exceptions here, so we are going to cheat a little bit, but that's the intention, right? If I ask for the head and tail of a non-empty list, I get the head element or the tail element. Otherwise, I do something else. So let's see what we do here, right? So we know that the empty list is lambda c, lambda n, n, and the non-empty list is a construction like this, right? It takes a cons constructor, null constructor, and applies the function c to h and t, right? And if I want to extract h out of this, right, what do I do? The trick is this, right? We know we have a function, true and false, which can extract the first and the second element of an application, right? If c were true, then it returns h. If c is false, then it returns the tail, right? And that's the trick that we are going to do. So we are going to define the head function as something that takes a list, right? Lambda L. And we know that a list takes 2 arguments, right? It takes a c and an n. It takes a c and an n. So for the first argument, we are going to pass true because we are going to extract head. So if the list is non-empty, right? So we are going to substitute true for C. So this becomes true, right? I actually don't care about the n value, but I'm passing nil here, right? Why am I passing nil? If the list is in fact empty, I can't throw an exception. I have to return something. So I'm just going to return nil as a result, right? So the behavior is not perfect. I mean, it is untyped, so it is sort of returning a nil. That is fine. But I'm sort of filling in the gap for the fact that I don't have exceptions in my lambda calculus at this point, right? So the idea here is head function returns the head if the list is non-empty and returns nil, right? The nil constructor if the list is empty. And similarly, if the list is non-empty, then because we pass a false here, we get the tail out. If the list is empty, then we get nil out. Okay, so that's the encoding here. So let's see how it works. So again, recall that L2 is 2 and 1. So if I ask for the head of L2, I should get 2. If I ask for the tail of L2, I should get a list, a singleton list, which contains 1. If I ask for the head of nil, empty list, I should get nil, because that is how we encoded it here. And similarly, if I ask for the tail of an empty list, I should just get nil. Right? So that is what we get here. So if I ask for the head of L2, then I should get the value 2. So I get the natural number 2 out, right? If I ask for the tail of L2, I should get a list out, right? I get the singleton list, right? A list contains takes a C and an N. The constructor is cons and nil, and it's a non-empty list, right? Because it applies C to some value. The value is 1, right? The value is 1, S of Z. This is the 1, and the tail is nil, right? This is the nil constructor. And in the last two cases, you just get nil out. Okay, so that's a simple function that extracts the head and tail. And yeah, okay. So I've destructed it. I also want to test it, right? I want to check whether a list is. I may want to check whether a list is empty or not, right? So I define this function called list nil. So the idea is that if you apply this snil function on a nil value, it returns true. If you apply it on a non-empty list, which has a cons, then it returns false, right? So recall the definition of is0 function, right? Is0 function, we defined it like this. It takes a number, right? And then we apply this function for s position, which takes a y and always returns false, because if you find an s in the construction, then it is not 0, right? Otherwise, we return true. We do a very similar encoding here. So isnil takes a list, right, L, and for the C position, we know that C takes 2 arguments. I actually ignore those 2 arguments. They are just lambda x, lambda y. I don't use that argument. I just return false, because if there is a C present in that encoding, then I know that the list is non-empty, right? So I just return false here, which is similar to the encoding of is0, right? And for the nil position, I return true. So if you apply isnil to an empty list, right, this gets substituted for C, but I don't have a C there, so that gets thrown away. And for n, I substitute true, right, and the result will be true. So that's the encoding of isnil. So here is just the encoding written in OCaml syntax, right? And I can ask for whether L2 is nil. We know it is false, right? And nil should be nil, right? That is true. So you get a false and a true. Okay, so that's the test. And the last thing that we are going to see is use this in a non-trivial fashion, right? So we've written in assignment 1, you've written lots of examples using lists, right? Lot of recursive functions using lists. A simple recursive function is computing the length of a list, right? So here is the function for computing the length of a list encoded using just the lambda calculus that we've seen so far, right? So it is also going to use the Y Combinator because length is a recursive function. So what do we do for the Y Combinator? For using the Y Combinator, we take f as an explicit argument, right? That is going to be the recursive function. Length takes a function, length takes a list as an input. If L is nil, then the length is 0. Else it is the successor of f applied to the tail of the list, right? This is, at this point, this definition itself shouldn't surprise you, right? So here is the encoding. So I'm using, I'm encoding S nil L here as a condition, right? S nil of L. And then the false case is successor of f applied to tail of L. So successor of f applied to tail of L, right? And the true case is just 0. True case is just 0, right? So I put it together. So the test condition, the true branch and the false branch, and I want a recursive function. So I apply the Y Combinator here, right? Now I have the length function. It's big, but that doesn't matter. So the length of the empty list should be 0 and the length of L2 should be 2, right? Let's see if that works. It does, right? So we get the length of empty list to be 0 and length of L2 to be 2, right? So at this point, I hope that I have convinced you that you can encode arbitrarily complex programs using lambda calculus, right? We have recursion, we have all the sort of tests. We've encoded booleans and natural numbers, but there is no reason why you cannot encode floating point numbers and say binary digits and so on. I mean, all of this just needs to have clever bitwise encoding, right? And we've encoded recursion, we've encoded algebraic data types. So there should be no surprise that you can encode everything that you want, right? Just using lambda calculus. So lambda calculus is Turing complete, right? And all of the examples that you've seen should tell you that it is as powerful as the languages that we have, right? We use to program in our everyday life, right? In terms of able to encode what they do, not do it at the same performance or so on, but really encode everything that the real language does, right? But we don't use lambda calculus as it is, right? The programs are pretty slow. So if you want to encode, say, 10,000 plus 1, we don't have, we've encoded everything as primitive. We don't have any primitive values. So we've encoded everything using these lambda terms. So if you have 10,000, it has 10,000 SS and then like a 0 at the end. And simple additions will require thousands of function calls, right? Just doing 10,000 plus 1 requires thousands of function calls. It is also pretty inconvenient in terms of readability, right? I cannot even pretty print these numbers. I mean, these are things that you can address, but it's not a real language that we want to program with. It is useful for reasoning about certain features that you might want to implement in the language, right? If I want to implement an advanced feature, I should be able to reason about it, encode it, and show that it works just using lambda calculus primitives, right? That's the idea here. And in practice, we use richer, more expressive languages like OCaml and Python and C++ and Java and whatnot that include built-in primitives, right? We want to compile these languages efficiently to what the hardware provides. The hardware provides registers. It provides like primitive operators that can manipulate these values, right? And we want to take advantage of all of that. So we don't directly encode everything in lambda calculus. So that sort of finishes the lambda calculus, untyped lambda calculus lecture, right? So what we've seen is we've seen how to take lambda calculus and encode non-trivial programs. Okay, so that is the lambda calculus encoding. Any questions on this one? I think there is a lot to take in this lecture, and not everything that you can sort of understand just by sitting through the class. But what I hope you would take away is that the power of lambda calculus, right? And then focus on simple examples. You don't need to. I won't ask you to. So the thing that I asked in I think quiz 1 in the last year was take this list encoding, right? And then encode something for a binary tree, right? So this is what I had asked. If you wanted to encode a binary tree, how will that encoding be, right? Um, so I won't ask you to encode some new thing like Boolean or something, but I might ask you to encode something that is a simple extension of what I've taught here, right? So yeah, so if I ask you a clever encoding, I might even not know the answer, right? So I won't ask any of that in the quiz, but sort of go through this and get the intuition behind how this works, right? So that's what I want you to do in this lecture. I have 5 more minutes, so I will just start the next lecture, and then I'll anyway continue tomorrow as well. Okay. So far, the lambda calculus that we've seen is untyped, right? So we have no types. There is no static checking. In particular, we were able to, we were sort of carefully working on only writing down correct terms, right? So there is no type safety. So you can go terribly wrong if you pass a function that takes 3 arguments where you expect 2 arguments, right? I sort of cleverly avoided all of that. But languages like real languages, right? OCaml, Haskell, and C++, and Python, and say Java have types, right? And so in this lecture, what we will do is we will add a very simple type system on top of lambda calculus. So lambda calculus is a very small language. So we will add a simple type system on top with the hope that you can appreciate what type systems bring for a language, right? So that's the takeaway there. So we will study it in the small, right? And the hope is that by studying type system, a simple type system, just for this very small language, you can appreciate what type system brings you. And we will study a bunch of concepts as well, right? Some principles that we can already see in this very simple language. Okay, so the yeah, so we call it simply typed lambda calculus because we use simple types, and we will see what those simple types are. So consider this untyped lambda calculus, right? So as someone observed in the last class, the encoding of false was the same as encoding of 0, right? So we have no, we can mix these two things together, right? Where you would have expected a natural number, you could pass a false, and that would have been fine because the encoding is the same. But we can also misuse the terms, right? I can apply false to 0. False is supposed to be this thing that you pass 2 values for, right? But if you just pass 0, you'll get an identity function. It's not clear whether you're doing something interesting here. And you can also write something like if 0 then, right? Test if 0 then. This is not going to work, right? So this is actually this will work, but you are mixing up terms here. So this is not something that would be accepted by the OCaml compiler, because everything evaluates to some functions. You can mix up places where you expect 3 arguments to what you do with 2 arguments, right? So this this sort of creates a lot of confusion if you wanted to program with this language in the real world, right? And the same thing happens in the assembly language. In the assembly language, everything is a machine word. It's a bunch of bits. So all operations take some machine words and implement other, return you, modify other machine words. So unless you are pretty sure what you're doing, you can easily make lots of silly mistakes, right? And the hope is that you can avoid a lot of these mistakes by adding a type system on top, which will catch most of the errors at compile time, rather than you running the program and then finding out what things go wrong. So okay, so how do we fix these errors? We use typed lambda calculus, right? And we are going to take the lambda calculus syntax, right? Just the expression language that we have seen in the previous class. We are going to add types on top. And what we end up getting is what is known as simply type lambda calculus, right? We use the symbol lambda um, superscript arrow whenever we want to identify simply type lambda calculus. But that's just I mean, we only use that because this is too long, right? And I might also use STLC if it is not clear what sort of lambda calculus that we are using. So okay, so I think I will stop here, and then we will start seeing simple types on top of lambda calculus and what they can do in the next class. If you have questions, I'll just hang on for a minute and then I'll wander off. Then you can ask questions offline as well. Stop recording.